guess that is a yes. All right. Can you see the screen? Just making sure. Yes, wonderful. All right, so I'd like to go over packets 7 and 8 today and partially on Thursday. This will wrap up everything you need for assignment number 2. And the main topics are thermodynamics, which is packet number 7, and material science or material theory, which is packet number 8. All of this is the remainder of chapter number 5. And we're basically in section 5.4, which is thermodynamics. So let's go over the basic ideas here. The main points from last time in class were essentially that we have this idea of the potential energy and kinetic energy and work that, if added together, provide us with a new state variable of the material in a given different period of time. So pictorially, what we have is we have a object or a system like shown here. We have time t equals to t1, and inside of this thing we have a potential energy at time t1. Then we also have a kinetic energy at time t1. And then we have some kind of work that we add to it, W going from state 1 to state 2, and this equals to this new state, and let's show the object deformed quite a bit, where it has now a new kinetic energy at time t2, a new potential energy also at time t2. And pictorially, the way this looks is I at state number 1 plus K at state number 1 plus delta W from state 1 to 2 is equal to I at 2 plus kinetic energy at 2. And if we bring this to the other side of the equation, bring this to the other side of the equation, and divide by delta T, we get what we see here at the left-hand side of the panel. We get what is sometimes referred to as the power equation. And this power equation basically states that if I take delta W divided by delta T, and then the limit becomes dW dt, this is equal to the summation of all the things that are introducing power into the system. Of course, the time derivative of the work with respect to time is, of course, the power. So units are important in this kind of a discussion. The units in this case are, of course, joules or energy. Watts are joules per unit second. So that's going to be, our metric of power. So we're always going to be thinking about watts as joules per second, which is power. And then, of course, joules is going to equal to energy. So the equations get somewhat complicated because the details are going to be hidden in the fact that each of the things that are hidden in here, I, K, W, I2, KW2, are actually going to be relatively complex integrals that take into account all of the different possible entities that are going on within the control volume. So for example, kinetic energy, if this had been an entire rigid body, that would have been a pretty easy affair as undergraduates, because we know that's just going to be 1/2 mv dot v dot, where there's a single velocity for the entire object, and it basically moved as a rigid body. That's obviously not going to be the case now for a continuum, because each little piece of material is moving with a different velocity, and therefore we have to integrate over all of these little pieces to compute the total kinetic energy. That's just one example. Then we have things like potential energy, which could be energy stored at every point in the body. That might be chemical. It might be elastic or strain energy. It could be photo-optical. There could be many different sources of energy that are stored up at all of these different points. Again, we're going to have to integrate over all of the little points in the body. Same thing with the work. The work is applied in many spots. It could be applied to the surface because it could be deforming this object in a variety of different ways. And it could be magnetic forces or electrical forces that are latent within the material because perhaps some current is running through this thing, as we've seen in the simple examples of the robot and others. So all of this stuff together when we add them together, is going to give us the power equation. And in its most simplest form looks like this, but it's going to have many different pieces to it. So let's write this out explicitly and then start to explain exactly each of the components. So we have dW dt is equal to the mechanical power. I'm going to separate that into several different pieces. We're going to also have the heat flow. So there's going to be heat flow into the system. I actually have used the symbol Q. Sorry about that. So the symbol Q is going to be heat flow, and that's primarily going to be conduction, although there could be other entities like radiation and things of that sort. We'll just assume right now that the only component there is conduction, and we'll specify that in a moment. And then there's heat sources, which could be things like, for example, sources. The best example, of course, here is a laser. So for example, input of optical energy and things of that sort. So all of these things together basically are the power input into the system, and they are exactly the di dt plus the dk dt. So those two entities that we derived here on the other side of the panel, when we decompose them, we're going to decompose them into those three pieces. And so what we want to drill down to now is, let's write out explicitly what those components are. So the very first one is a pretty straightforward one. As I said, kinetic energy we know well from undergraduate mechanics. This is going to be, however, in this case, 1/2 V dotted with V d omega, where omega is the little volume. So we're going to isolate this body, and we're going to take a little control volume out of it, and we're going to call that little rascal W. So that, or omega, that little omega is the thing that's right there. Okay, so we're going to isolate one little piece of material. So the piece of material, let me zoom on it here, has the domain omega. The boundary is partial omega. It's going to have traction vectors on its surface, just like we had for the stress analysis. It's also going to have potentially heat flow. So it's going to have heat going into the system, which will use the symbol little q. And then also it has an outward normal, and that outward normal we're going to call n. So those are the usual symbols we'll use to describe exactly what's going on with these three pieces, H, Q, and P. So the first one, as I said before, is the kinetic energy, and it looks hauntingly similar like what we do for lots of rigid little bodies, except that we have, in this case, we have the volume, which is shown here. It's the d omega times rho. That's the little differential mass. And the little differential masses are all multiplied by their little v's. So let's make a note here on the side. Suppose we had 1/2 mv dot v dot. We know that that's the kinetic energy for a little ball or a little point mass that's moving through space. Now what we're going to do is we're going to take an integral of all of these little guys together, and we're going to add them up. So pictorially, that's exactly what this integral is representing. These are the little masses, the rho times the volume, and the little velocities are each of the velocities at every point within that domain omega. Okay, so that was a pretty straightforward one. The next one is the I. So if we look at I, which is the potential energy, that thing is going to be integrated as rho times something called W. So don't confuse this with omega. That's the stored amount of energy per unit mass. And we're going to again integrate that over d omega and integrate it over the volume. So what that represents is that at every point inside of here, these little points inside here, there's a little amount of energy stored up in there. And I'm going to be non-committal as to exactly what they are. I'm simply going to say, I take a piece of mass, I take the amount of energy that is stored in that little body, and I'm going to add them up by adding them up over the whole volume. Okay, so again, pretty straightforward for that as well. No biggie there. Now, where the trouble starts is, what are these other quantities like P, Q, and H? So if I look at, for example, P consists of many different things. It's the integral of, for example, all of those body forces that we saw last week times the velocities integrated over the little volumes, plus the integral of the surface forces. And the surface forces we know now are equal to the traction. So this is the traction vector, T, multiplied by the velocities on those bodies integrated over the little areas. So let's do a deep dive on what we mean there. So number one, we have little body forces, F's, that are acting all over the place. Those are those little F's there. And if I take the F and I multiply it by the velocity that is happening right at that point, and I take their inner product of F and V, we know that to be equal to power. As undergraduates, you've learned all kinds of stuff. For example, if you remember the classical case of a box, you're pulling on the box with some force and there's a velocity, and that velocity is multiplied times the force that accelerates that object. So the force times the velocity, that of course is going to be equal to the power, okay? That's exactly the decomposition we have here. We have force times velocity, but we add them all up over the little body, as we're seeing here. That's the first part that is due to mechanical forces. Now, there happens to be also forces on the boundary, as we know. Those are the traction vectors, T. And if we take all of those little traction vectors and we multiply by all of their V's and we integrate it over the area, we get the second component of P. Hence, we have the third little piece in our puzzle. We have the power that's due to mechanical forces there. Okay. Now, Q, as I've indicated here before, Q is going to be equal to the heat flow in the system. So if I come and I take now the decomposition of that, Q is going to be equal to the flow through the boundary of my little control volume. The vector of heat flow is Q. I multiply it times its normal to get a direction. So keep in mind, I have my Q and I've got the outward normal here, and I'm going to take the inner product of Q and the outward normal. So I'm going to take N dotted with Q, N dotted with Q. But since they're pointing in the opposite directions, I have to put now a minus sign so I can get the flow into the control volume. So critical point here, this is the outward normal. This is the inward flux. The outward normal times the inward flux, since they're pointing in the opposite directions, I have to multiply times a negative sign. Oops, sorry about that. Times a negative sign Q to be able to get the flow into the system. And I integrate all of that stuff, of course, over the little area dA. Now, I can rewrite this because I know Gauss's divergence theorem. I can immediately take this, and let me just clean it up again. This is Q dotted with N. And I can immediately write this as the partial of omega turns into omega, the volume. I have the divergence with respect to x of Q, and now this becomes a little d omega, and I have a minus sign. So that's Gauss's divergence theorem, which helps me quite a bit. Now, the final little piece, so this is the heat flow. That's the other component. So far we've knocked off the I, the K, the P, and the Q. We have one last thing here remaining, which is H. And that one's going to be a pretty easy thing to characterize. We're just going to write this as the amount of energy that is added as a source term. We'll use the symbol Z times the little differential volume integrated over it. And that's basically, if we're thinking about the control volume, all that's saying is there's a certain amount of energy that is added by some mysterious source to each of these points. It could be through electricity, it could be a laser, it could be some chemical reaction. All I know is it's given by this amount, Z per unit mass, and I multiply it by the mass, which is shown here, and that's the final component. So this allows us now to have characterized everything in this equation, which leads to a gigantic integral equation. Now, I'm not going to bore you with the algebra because it's pointless to do online.
Apologies, Tarek.
Yes.
What is the Z again?
Z is the amount of energy per unit mass. So let me write
Okay.
that. Z is energy, or actually power. Sorry about that. Power input per unit mass. Okay, so all of the symbols, Daniel and colleagues, are all shown here. The integration is pretty straightforward. What we did is we basically derived everything that's shown there. We then basically have to use the integral tricks that I showed you before, which is we basically manipulate taking the derivative now of lots of these integrals because we need to do that. And that arises from the fact that we have our dk, di, dt, we have derivatives of all those integrals. So keep in mind, when we look at the things we had on the previous page, we derived the integrals here, integral, 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 integral. But unfortunately, we have to take the time derivatives of those integrals. So what that means is I need to come back now and take a ddt of all of this stuff, a ddt of many of these other terms, which means I need to use the tricks of converting integrals into reference configurations and time invariant configurations, because my volume that I'm integrating over is actually a volume as a function of time. So the problem is, if I were to come cavalierly here and take a time derivative of this integral, I would also have to take a time derivative of that boundary integral, which is a big pain. It can be done, but it is not easy. So it is better to convert this into an integral over some reference volume that doesn't change, which is not a function of time, and then bring the derivative inside and take the derivative of all the junk inside. And that's in fact exactly what we do in this term here. So in the manipulations here and using the manipulations here, we do exactly the same thing with the time derivatives. So I want you to go through that exercise. It's not a big deal, but it is a little bit of tedious algebra. It's not that you're going to be tested on trying to derive this stuff, but it's good to understand the manipulations, to understand how these equations are generated. But at the end of the day, when we get down to it and we collect up all the terms, we get one gigantic integral that looks like the following. And it's important to write it out. It looks like d omega, or sorry, integral of omega of rho w dot. So again, this is the density. And this is the important part that you need to focus on. That's the density. This is the stored energy in the body. So then it's time derivative plus the velocity of every point in the body times the density times the velocity's derivative with respect to time plus, minus the divergence of the stress plus the body force. So again, getting ahead of myself, minus F, all of that stuff, close parenthesis, minus sigma dotted with the gradient of the velocity plus the divergence of Q minus rho times Z, close the parenthesis. So let me put the parenthesis over here, d omega equals to 0. Now, this integral at first looks highly intimidating, but it has a couple of nice features. Number one, last week we derived the following equation. Divergence of sigma plus F equals to rho v dot. That's the balance of linear momentum. That helps us because it actually appears here in disguise in between these parentheses. So if we look at this and we compare it to that, it turns out that this is equal to 0. Therefore, this is equal to 0. So this entire term drops out and we're left with this extreme simplification. The simplification now looks like the integral of rho w dot plus, minus sigma inner product with the gradient of v dot minus the divergence of q plus rho times z, close parenthesis, d omega, and this is a w, omega equals to 0. Now, this is a super important equation, probably the most important equation in this class. This is the so-called power equation. Okay, and you've seen it as you will see shortly in many different forms, although you may have not realized you've seen it. Now, the important thing about this is what this states is that this integral is always equal to 0, regardless of where you pick the control volume. What that means is when I started out this analysis and I said, let's focus on that little control volume omega, I could have picked that here. I could have picked it 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 in any weird shape. It's completely arbitrary. Since this term is arbitrary, but every time I integrate whatever is here, it adds up to 0, the immediate conclusion is that rho W dot is equal to sigma times the gradient of V, excuse me, no dot there, pardon me, the gradient of V plus the divergence or minus the divergence of sigma, or sorry, Q, plus rho times Z. Now, that simpler form of this is important because what it allows me to do is it allows me to characterize each of the terms very carefully. So this is the important part that is critical to assignment number 2 and to getting a further understanding of the implications of this equation. This is the density in the current configuration. It changes with time. This is the energy stored, and it's also its time derivative. So this is energy stored, time derivative. This is the actual stress that we have encountered before in the balance of linear momentum. This is the velocity of the piece of material. This is the heat flow into the system, and this is the amount of energy added, so from sources, okay? Now, this equation has a lot of beautiful implications. Number one, it tells us that it's interesting that the equation here, the stress appears here, and it also appears here, which means that things that control how things deform and the balance of momentum also have some role to play with the energy that's inputted into the system. So what's weird about this is that whenever I take a piece of material and I stretch it back and forth and I flex it, and for some reason, if I did this a lot, this hinge would get really hot, right? If I kept doing this over and over again and just keep oscillating it back and forth, if I did it long enough, this entire material is going to fatigue and get very hot and break apart. There's no heat input. So at first one is puzzled by this as an undergraduate. Where did the heat actually come from? Well, the heat came from this so-called thing that we refer to as the stress power. This is called the stress power contribution. And the stress power contribution says the magnitude of the stress inner product with the gradient of the velocity, that product of those two things lead to an increase in the amount of energy that is inputted into the system. So let's take a closer look at that thing. What that thing says is, if I take an object and I start oscillating it back and forth, so let me isolate this little piece of material, and I subject it to a high value of stress, but I take the product of the gradient of the velocity with that stress, this will lead to some kind of power increase in the system. How does that work? Rho W dot is equal to sigma times the gradient of V, even in the absence of no heat input, divergence of QF, suppose I put no heat input, even in the absence of any source input, for example, no laser and so forth, if I just looked at the contribution of these two terms, the amount of energy that increases in that location there is directly related to the product of the stress, and the gradient of the velocity. Now, the implication there is pretty weird. What that really tells us is that if the velocity is uniform, if this was one entire big object with a uniform velocity, this term here would be equal to 0. So that means that if I take this object and I just move it around rigidly all over the place, it's not going to get hot. It's not going to have any stored energy because it's not actually got a gradient in its velocity. Every point has the same velocity. There's no gradient of the velocity. So that's the first important thing to understand, that the body itself is not having any gradient of the velocity. Therefore, this term here would end up being zero. At the same time, if the body had no significant stress, let's say it was a floppy piece of material like this, piece of cloth, right? And I just oscillated back and forth and back and forth. How big is the stress in the cloth? It's practically nothing. So it takes two things to have to come together to make some energy happen. Is the stress multiplied times the gradient of the velocity. That combo then leads to some increase in the power. And that's the first epiphany that we should have in this thing, is that there is a definite interplay between stressing somebody and making the body start to have some heat. And that, of course, we've seen it in medieval movies where we have, some kind of a metalsmith that's sitting there with a hammer and they're mashing an anvil and they're making a sword, and the thing is getting hot, and then they take the sword and they dip it into ox blood. And of course you wonder, well, was it hot because the person took it out of the furnace and then heated it up? It would have been hot even if the person was banging on it with a sledgehammer with no heat. Of course, heat helps make the material more pliable, but just the stress alone from the impact of the hammer will increase the temperature of this dramatically. And of course, you can test this all the time. If you take any kind of hammer or hard object and you bang a piece of material and then you touch it, of course, it's scalding hot. So this is an extreme amount of energy that is input due to the mechanical changes in the material. So this equation is important enough for me to write it one more time very neatly here, because it has some implications also that make it a little bit more important than just simply an equation that is at the points inside the body. So let me draw a little cartoon. This equation here is valid at every point inside the deformed object in the current configuration. So when we're drawing our little cartoon of 2 weeks ago, we started out here in the reference configuration, and then we said it stretched, and it starts over here and it goes over here. This is in this location here in the current configuration. So this is a snapshot of the object, and at every point inside the body, this is the equation that holds. So what we're going to see later in the semester is we're going to use this equation over and over again, because we're going to basically take a laser, for example, shown here, and we're going to zap this thing and hit certain points in the body and heat them up. Well, the way we account for the laser is exactly from this term and this term, from heat conduction and heat input. This is a pretty flexible equation because it allows us then to start to characterize for different manufacturing processes, different types of Q, different types of input, different types of stress, different types of material storage. For example, this could have been a battery, right? It could be a battery system where we have some mechanical separator, we've got cations and anions on one side, and the electricity is flowing back and forth through the separator. That, of course, leads to all kinds of heat buildup. That's how batteries get hot. So this equation is also the equation for batteries as well. So the heat buildup from flow of electricity through a system is also included in this kind of a system as well. So we need to keep in mind that it's a generality and we will tailor it later. Now, there's one sad thing about this equation. What can people tell me about the equation?
It's nonlinear.
It's super nonlinear. I mean, if we thought this thing was a pain, the one I'm writing here, this thing is even a bigger pain, that it's got all kinds of crazy stuff going on. It has potentially weird input from here from a laser. It's got heat conduction over here. It's got the product of the stress and the velocity. That's going to be super nonlinear. So it's No telling what kind of craziness is going to go on there. And then it also has the energy storage. That means that this equation here, the balance of momentum and the so-called power law, they're coupled, strongly coupled. So these things are really coupled together, which means unless you do some simplifications, you can't solve one equation without the other. So you'll see in many doctoral theses, just these two equations enough pretty much drive an entire thesis, let's say in theoretical mechanics, because it's an extremely rich area of trying to figure out how the stress here interacts with the stored energy and vice versa. And of course, all kinds of devices exist. Thermoelectric devices, these are the two equations. So if you're thinking about two equations, thermoelectrics, they are governed by this. If you're thinking about equations for battery swelling, for example, many of you may be interested in batteries and things of that sort, it is exactly these two equations. Now, under normal circumstances, these equations are unsolvable, but of course we have all of the tools and the finite element machinery that now in a modern, engineer's repertoire, she can easily deal with these things, in the following sense. You can basically take any kind of a system, you discretize it with some kind of a grid, and you can solve these things mechanically. Now, if we rewind 50, 60, 70 years ago, again, we're faced with the engineering dilemma that in many cases, this equation becomes unsolvable because it's over here now in the deformed configuration. It has two nonlinear equations now, highly nonlinear for the stress, for the velocity, all of these terms. Engineers decided, you know what, let's use that same trick as before. Let's rewind this to the reference configuration. So this is the current configuration. This is the reference configuration. And let's attempt to recast the equations over this referential state. Now, we already did it last week for the stress. We converted this thing into the divergence of F dotted with S plus F multiplied times the Jacobian equals to rho zero times the velocity dot. That's the analog to divergence of stress with respect to the little x plus F equals rho V dot. So those two equations are one and the same. One happens to be in the current configuration and one is in the reference configuration. It turns out that we can do exactly the same thing for the first law of thermodynamics, or the so-called power equation, that this equation, rho W dot equals sigma times the gradient of V minus the divergence of Q plus rho Z, can be rewritten in a nice form of rho dot W dot S times the derivative of E minus the divergence of Q0 plus rho 0 times Z. This happens to be again in the current configuration, and this is in the reference configuration. And let's see what the differences are. Well, this term here happens to be the absolute deformed density. Keep in mind, we have an equation, rho J equals rho 0. So we can always figure out, if we know the original density and we know the Jacobian, and the Jacobian is the determinant of F, we can immediately take that equation and manufacture from there the new density. The new density would just simply be the old density divided by the Jacobian. Okay, now that is what I'm highlighting, the differences here and here. It turns out the next term, the rate of change of the stored energy, is really the same one in both equations. That doesn't change, and I would ask you to please go through the proof so that you can prove it to yourself. That's important. Number two, the product of the stress with the gradient of the velocity through all of these different manipulations, which are shown here on the left-hand side, ends up becoming this following term. It ends up becoming that funky thing, the second Piola-Kirchhoff stress, again, that weird term that is sigma is equal to 1 over J Fs Ft. That's our good friend. It makes a cameo appearance here as S. It turns out there's another cameo appearance. There is E, and E is equal to 1/2 F transpose dotted with F minus I over 2. That's the Green-Legrand strain. So there's a product between the Green-Legrand strain and the second Piola-Kirchhoff stress. That product between the two basically produces those two things, okay? Now, the nice thing about this is that we have then the heat flow in the system, and the heat flow in the system is slightly different, but there's one key component. It's the gradient with respect to the X that is shown here, which we know because we know the original configurations, as opposed to taking the divergence with respect to the current X. So the same selling point that we made in these equations where we said we take capital X and little x shown here, we basically have the same thing that appears here and here as well. So it's a wonderful thing that occurs because what we basically have is we have an equation where we know what we're taking the derivatives with respect to. So when that was first derived, probably around the early 1900s, this was a breakthrough in the ability to try to solve these equations in some limited capacity. Now, there's good news and bad news. It seems that it's a little bit easier because the configuration is one we already know. So if you were thinking about solving an equation where you said, look, I have a bridge and I've got some loading, perhaps it's a train or something else from the early 1900s, and I want to determine how hot the supports are going to get because they might get hot and mushy and they'll buckle easier. That was the typical thing that this equation was used for because people were very concerned about thermomechanical buckling. As you can imagine, you take a skyscraper, and these were first developed starting in the early 1900s by Carnegie. Steel had been first perfected, and of course, you're thinking about some kind of a high-rise building and you have all of these metallic struts. And if you're worried about a fire or some other thing in the system and the struts start to get hot and soft, they can easily buckle if a load is applied to them if the material is hotter. So this equation was the one that came to the rescue. This equation was used day in and day out to figure out whether we were going to have thermomechanical buckling and failure of that sort. The problem is, provided that the stresses are pretty small and the deformations are small, you can toss this term, right? Because if the strains are small, the object isn't deforming very largely, then you can take care of this term and this term never appears. So the first, stinker in this equation is that this term is gone. The second term is if there are no lasers or no heat input, that thing is gone, and you're left with a pretty simple equation. This thing and this thing, which I'm going to highlight for you because it has great implications for us. The implications are the following. Rho 0 W dot is equal to, in this case, the divergence of Q with respect to capital X and a minus. Now, if I make some pretty simple standard assumptions, we've learned as undergraduates that when we take an object and we have some heat that flows through it, what is the relationship between the heat flux and the temperature? There must be some relationship between the two. The one that usually comes to mind is so-called Fourier's law. Fourier's law simply says that the heat flux is equal to something called the conductivity times the gradient of the temperature. And since things go from hot to cold, we put a minus sign here, which means that if the gradient of the temperature is big, there's this positive constant that tells me how the heat is going to flow. So in other words, if it's hot over here and it's cold over here, heat is going to do what? It's going to try to go to cold. Now, that's not entirely obvious. For a long time, even currently, people are always fantasizing that there is potentially some kind of funky material or some funky set of events that you can make cold flow to hot. Now, if that fantasy ever comes to fruition, that changes everything in engineering because we don't need heat anymore to make refrigerators. They just get cold because this magical material gets cold when we want it to, because cold goes to hot. Uh, that means that we don't have losses. So for example, if we had electrical wires where somehow they never get hot, in fact, they can even get colder, that's awesome. Why? Because electricity loves cold things. It flows a lot better when the material is cold because it has less internal resistance. So there's a lot of things that if that were to happen, it would be, a real boon for society. Fruitlessly now, for 150 years, since science has really taken off in this area, people have been unable to find such a material or such a state. The closest thing they have are the so-called superconducting materials, as we'll talk about a little bit later when we get to electricity and magnetism, which simply means that there's almost no loss in the material as the electricity flows through the system. Heat flow is very similar. We don't know of any material where when you heat up one end of the material and you have the other material cold, where the gradient is basically hot to cold, everything we know is that there's something that flows from here to here, and the amount that it flows at the rate is given by the so-called conductivity. Okay, that's so-called Fourier's law. Now, Fourier's law has a lot of, nuances to it. For a 1D stick, if this was just simply a wire, it's pretty easy to characterize. There's usually a single piece of material or material parameter called the conductivity, and the flow of heat is in one direction. Now, if we start to consider a more complicated body where it's a complicated geometry and the flow of heat can start to move in many different directions, right? The problem there is we need to have a much more advanced version of Fourier's law. So in 1D, the Fourier's law says the heat flow is equal to minus K times the derivative of the temperature with respect to X. That's a 1D version of this where X is in this direction. The 3D version of this, which I'll draw a little coordinate system for here now, X1, X2, X3, is equal to the heat flow vector, which is Q1, Q2, Q3, is equal to a matrix of constants, K11, K12, K13, K21, K22, K23, K31, K32, K33, multiplied times the gradient of the temperature, which is in this case is going to be the divergence. So we'll take the partial derivative of the temperature with respect to X1, the partial derivative of the temperature with respect to X2, and the partial derivative of the temperature with respect to X3. So that matrix equation, written a little bit more elegantly, says Q is equal to minus the conductivity tensor. So we call this the conductivity tensor, but it's really just the matrix of all of these constants, inner product with the gradient of the temperature with respect to X. Okay. Now, a couple of things about this conductivity tensor. Number one, it's a positive definite matrix. So it means it has positive eigenvalues. It is symmetric. And a Nobel Prize was given for this in 1932 to Lars Onsager. So that's not a trivial thing to prove. In fact, that the K is positive definite and that the K also happens to be symmetric, Lars Onsager, 1932. So not an easy thing to prove and not an easy thing to experimentally measure for many different materials. Number two is, because T is such a ubiquitous symbol, oftentimes we use another thing, we're going to call it theta. Now, the reason is that T is used for time, is used for traction, is used for all kinds of stuff. So to not confuse it at all, we're just going to give it the symbol theta. So everything we see here, just to make things clearer to see, we're going to call it theta. Okay, that's the temperature. Now, the temperature is a scalar. At any point here inside the body, at this point here, there's something called theta. It is a function of x1, x2, and x3. So it's definitely changing at every point inside the body, but it's a single number. It's a scalar. Even though it itself over here is a scalar, whenever we take its gradient, which is shown here, so let me rewrite it in terms of theta as my variable of choice, this is a vector. So the gradient of theta, also shown here, in fact, let me erase it and make it clean and beautiful, gradient of theta, that thing is a vector. This thing is a matrix. This is a 3x1 vector. This is a 3x3 vector. This is a 3x1 vector. Okay. Now, the important thing about this is a couple of things, that even though the heat, flows from positive to negative, I mean, from hot to cold, this material may have very weird flow patterns. And the flow patterns are important for our business in the Bay Area because all of the circuitry, all of the gadgets that we have in our laptops, our cell phones, and so forth have fairly anisotropic material properties. And the reason is that we want the heat to flow in certain directions. So in fact, let me draw a laptop for you. All right, if I draw a laptop like shown here, and I look inside one of the widgets or gadgets, let's suppose it's a circuit board of some kind, I might want the heat, if the material is getting hot here and is cold there, I might want the heat to not necessarily flow directly to here, but I might want to bend it towards a possible fan. Now, the only way I can bend that material is to start messing around with the conductivity tensor. That if these numbers, even though it's a symmetric matrix, I can mess around with K11, K22, K33 in such a way that I can guide the material heat flow in certain directions. As a very tangible example, if I take a piece of material, let's suppose it's PMMA or ABS, so it's just some kind of a plastic, and I come along now and I take some wires and I build micro wires inside this material at the small scale. So I'm drawing it exaggerated, but I put wires in a certain direction, and these are silver. Even though the heat might be coming from this direction, it's going to see the silver and do what? Well, it's definitely not going to flow against the silver. The heat is going to build up along the wire and it's going to start to get pumped in this direction. So the point is that material design at the small scale, meaning that I now have to zoom in on a piece of material, and if I put little micro wires in a certain direction at the nanoscale or even at the micro scale, I can start to make the heat do very funky things and guide it in certain directions. We're going to talk a lot about that in about 2 to 3 weeks, the so-called material design problem of figuring out how to make the material do something we want, even though each of the individual constituents, the matrix and the embedded material, might be standard, but because of the microarchitecture of the material, we can start to make it do things that any normal material would not. That's, of course, the robust world of material design. So please read packet number 7. Those are the highlights of it. What's important to also understand is that every single one of the terms in our balance of heat flow, this equation here, have different representations depending upon the type of manufacturing process. So this equation is so rich and robust, we can describe rolling, we can describe cutting, we can describe lasers, we can describe compaction. All of the different events are simply able to be described by taking different values or different expressions for these that are shown there. So in page number 4, we give you a very general description of exactly how we can decompose the so-called energy equation, the W that appears here. There are certain standard decompositions of how we usually like to describe it. We usually describe it as a piece that is entirely thermally based. So for example, if I take a piece of material and I come to here and I say, how much energy is stored at that piece of material? Usually the standard decomposition is there's a certain amount of thermal energy stored and there's a certain amount of mechanical energy stored. The mechanical energy is given by an equation which we're going to talk about next, either today a little bit and also on Thursday, which is the so-called stress-strain relationship. This is the classical Hookean type of energy. And then there's also something that is the thermal amount of energy. The thermal amount of energy is given by the following parameter. It is the density multiplied times the heat capacity times the temperature measured in Kelvin. That's very important. Kelvin is measured from absolute zero. So what that means is if I heat up the body a little bit here at this point, the amount of energy that's stored up is its heat capacity, the density that is associated with it, and then also the temperature of how much it heats. What that means is if I subtracted out this little piece of material and I came over here to a glass of water and I dumped this piece of material inside and it was really hot, what would it do? It would produce steam, right? And I could drive, for example, a propeller in a turbine and then basically make electricity. So the idea is that the amount of energy that I store up at a certain point can be converted into something else that might be usable energy by some third party. So what's very important in these kinds of analyses is that we have two compositions. We have the amount of energy that is due to thermally stuff or stuff that's stored up there, but we also have springy energy. And that springy energy is the so-called mechanical energy. So if I look here at a piece of material, deep down inside, it's a lot of little atoms with interatomic potential energy between them, right? So we usually draw these pictures, although it's somewhat naive. They're little zones or dots here, and each of the zones or dots have little funky looking springs between them. Of course, they're really not springs. They're highly complex intermolecular and interatomic forces that are governed typically by Schrodinger's equations and all of the other stuff in quantum mechanics. But, in a very naive sense, there's some kind of a spring constant, K. The spring constant K is multiplied times X times 2. We know that as undergraduates, if we take a spring and we apply some kind of a force to it, the spring constant K multiplied times the deformation of the body X, right? If I take those two products and I divide by 2, that's the amount of energy that's stored up in a spring. And we know that, of course, we've all had toys as children where we basically take a spring, you load it into a box, and then you perhaps launch a rocket or launch a ball or do something else. The amount of springy energy is converted to kinetic energy by the spring expanding. Well, guess what, friends? This is exactly the same thing. It's just the continuum version of lots of little springy guys that are associated with that point. That is exactly this piece here. So bottom line is the typical decomposition is one of mechanical part and then, thermal part and one of mechanical part. That's the so-called standard decomposition. And we're going to talk about that a little bit more in depth when we get into material laws, probably starting on Thursday. Now, let me give you one other example, which is a really good one and is a very important one, especially for those of us in the Bay Area that are working in advanced manufacturing. The first example is the so-called laser problem. So let's take a piece of material and let's see if we can use this law to tease out how hot a piece of material gets. So if I take a laser and I apply it onto a surface of an object here, I'm interested in figuring out how hot does this, zone underneath get. Now, many of us are interested in laser sintering, laser processing, all of these kinds of things. This is a very fast way to determine roughly how hot that material is going to get. So I'm going to call this laser input, okay? And I'm going to do the following thing. I'm going to first say, I'm going to go to my general equation, rho W dot equals to sigma inner product with the gradient of the velocity minus the divergence of Q plus rho Z. Now, I'm going to make a couple of assumptions to see if I can use this equation to get something, a quick, fast answer to how hot is this thing going to be. So to make things clear, I'm interested in determining, as a function of the laser input, how hot is this going to get and how long does it take to get hot? Okay, so the first thing is I'm going to say, you know what? Stresses and velocity of the material, it really doesn't do much. It's not going to get deformed a lot. So you know what? I'm going to toss this term. So I'm going to come over here and say, you know what? Gone. Okay. Number two, this thing is happening so fast, femtosecond laser, super fast, it flashes it. There's no time for any heat conduction. I'm going to throw that away too. Okay. I'm also going to say that the amount of energy that's stored inside of here is equal to the rho W is going to be equal to rho heat capacity times the temperature. Okay. So just as before, it's only the thermal part of the energy. I'm going to assume there's none that is stored mechanically because the stresses are small and are not really squishing the material a lot or pulling it apart. So those two things lead to the following equation. I'm left with rho C theta dot, okay, is equal to rho times Z. Now, rho times Z is actually the laser input in terms of watts. So what I'm going to do is I'm going to call this entire thing, I'm going to use the symbol I, which is I is equal to irradiance. So if you ever looked at the back of the label of a laser, I mean, if you looked at the back of a label of a laser, you see the amount of power wattage that a laser emits. That is in fact exactly this quantity right here, I, and it is exactly the equation or the term that appears in the so-called power law equation. Now, the nice thing about this is this immediately allows me to write out a very simple differential equation. Rho C theta dot is equal to I. Now, this is important because I can immediately rearrange this equation to say theta dot is equal to I divided by rho C, which means that if I integrate this equation, I get that T, or theta of T plus delta T, is equal to theta of T plus delta T divided by rho C multiplied times I. Okay, that's immediately, if I solve this equation, this is the term I get. So what this tells me is that if I integrate this simple differential equation, so I integrate both sides, right? If I integrate both sides, just to make things clear, let's write it out again here. This is d theta dt is equal to I divided by rho C. Okay. I take the dt to the other side and I'm left with d theta is equal to I dt rho C. I integrate both sides of the equation and I'm left with theta of T plus delta T is equal to theta of T plus delta T rho C I as a function of T. Now, let me turn on my light because the sun is setting first. Let's ask the following question. My boss comes along and says, look, we've got this object. We are going to zap it with a laser. You have a certain wattage, so you go and size for me a laser. How long should I lase this thing to get a certain temperature? So let's suppose we start out at, I don't know, 300 degrees Kelvin, roughly room temperature, okay, around there. And I want to get the heat of this thing, I want to get it up to 700 degrees Kelvin. How long should I lase this thing for? Well, let's see what the equation tells us. I have theta of T plus delta T, and I am going to set this now to be 700. This is equal to, I started out at 300, right? So I'm picking off the terms here. 300, 700. I have a certain amount of material, right? I have the density. So depending upon the material, I have a certain kind. This could be, for example, steel, could be aluminum, could be anything, but it's some value there that I'll have there. So we can assume, anything you like, take it, to be steel, for example, 700 kilograms per meter cube, or 7,000 kilograms per meter cube, some number. We have the heat capacity, again, for the specific piece of material. We have delta T, and we have the laser's intensity I. So what are the things that are variables in this system? Can anybody answer it for me? What are my play knobs? In other words, I got knobs here that I can turn on the widget and the dial. I can't change C. That's the material I have, so I'm stuck with that. So let's suppose it's for steel. I am stuck with the density of steel. I really can't change that. The target, I started out at 300 and I've been given 700. I can't change that. So what can I change?
The intensity.
Yep, I have two choices. I can either change the irradiance, super mega laser, and do it for a short period of time, or so-so laser and do it for a long period of time. Now, if the engineer, the boss says, you know what, you need to have delta T, we need to, flash this thing for just, I don't know, 10 to the minus 3 seconds, then that's gone. A millisecond, that's fixed too. So all we're left there with is then if we have d theta dt is equal to I rho c, and we have that equation, theta of t plus delta t is equal to 700, which is equal to 300 plus delta t, which I'm now going to say it's 10 to the minus 3, and I'm going to say it's rho of steel. So let's see, steel is around 700 kilograms, 7,000 kilograms per meter cubed, and I forget the heat capacity. Let's suppose it's, 200, some number like that. That's fine too. And then I have delta T, which is given, and I have I. So I can now back out, this number here is the one I'm after. I take 700 minus 300, divide by 10 to the minus 3, multiply by 7,000, multiply times 200, and immediately I can tell you what the laser's irradiance is. Now, let's review the magic. We started out from that god-awful equation here, the first law of thermodynamics, but we systematically said, well, stored energy is this. Okay, fine. We're going to ignore the heat conduction. Fine, get rid of that. That seems reasonable. If it's a very fast flash, it doesn't have time to conduct heat. Number two, we're going to say, you know what? We're going to have the laser. It's just going to be here on the surface. It's just a single number. So that's not going to change over time. It's just some single parameter. So we're left with then, we know what the target temperature is. We know what the starting temperature is. We know for how long. We know what kind of material. We back out I, and immediately from very general principles that started out in the beginning of the class, we go from the nightmare of control volumes and simple things like this. Then we end up getting that monster equation that's here. And from there, with simple assumptions, if we do them correctly in this example, we immediately can back out something very practical, like the temperature and the amount of irradiation that is needed. Now, it's important to understand this was a quick and dirty way to do it, right? This is making a lot of sweeping assumptions, but they're pretty good that if you were in the lab and you said, look, I want to figure out how long I have to laze this thing for, or what the intensity is, this will give you extremely accurate values of what the value is that's needed to heat up a piece of material on a surface. Now, if you said, look, I need to know more, I got to know how the heat is going to flow, and it's got to flow through some different complicated shape, and I need to know the depth and how long it takes before it starts to penetrate deeper into the material. Well, friends, then you're out of luck. We're going to have to solve this PDE, and that PDE is a handful. So we're going to come back to that a little bit later. But the ability to solve that is going to fall on many different possible techniques. One is called the finite difference time domain method. It is the go-to method in many of these kinds of analyses because it's geared towards things like laser analysis and things of that sort. It's actually even better in many cases than the finite element method for these kinds of problems. So I'm going to stop here for today, but we're going to pick up next with packet number 8, which is essentially the material behavior of material. Now, let's look a little bit about, I'll guide you through that for Thursday. What we're going to do is we're going to take the first law of thermodynamics and we're going to use this thing to actually generate a stress-strain relationship. What's weird about this, and usually you never see this as undergraduates, is the first law of thermodynamics, the so-called power equation, if you interpret it correctly, also tells you how the material should be behaving. Now, that important piece of information, we're going to be able to use this equation, rho W dot equals to sigma inner product with the gradient of V minus the divergence of Q plus rho Z. Incredibly, that thing is going to give us stress is equal to elasticity multiplied times strain, Hooke's law. So Hooke's law that we all know and love as undergraduates is actually going to be derived by the power law equation. And that's what we do in the beginning of lecture on Thursday, is I'll show you exactly that we're going to get this equation, and it is not a choice. It turns out that Hooke's law were forced upon us. Under certain assumptions about the thermodynamics of a material, Hooke's law has to hold. It isn't an option where we say, well, I'm going to guess it's elastic and therefore, it's an assumption. We do that often as undergraduate studies and strength of materials and things of that sort. Usually the assumption is, let us start with Hooke's law as if it is somehow a choice. It turns out what we find out from the thermodynamics is it isn't a choice. You have to have Hooke's law under certain assumptions. Now, once the assumptions go away, meaning that the deformations are big, they're fast, you've got elastic and viscoelastic effects, you might have plasticity, you might have damage, then you have to start augmenting Hooke's law. And this thing right here is not good enough. So you start to have Hooke's law plus some modifications. Okay, and the modifications start to include plasticity, damage, nonlinearities, which real materials exhibit. Now, for most analyses, Hooke's law is pretty good. In fact, if you went to Boeing, although I'm not sure we have confidence in Boeing these days, but Boeing, when it used to be really careful about doing its stress analysis, uses Hooke's law remarkably well to be able to design engine casings, airplane wings, rudders, things of that sort. There's a variety of things that Hooke's law is invaluable for. So we're going to spend a lot of time, well, actually all of Thursday on Hooke's law, because we really need to master that thing and understand it, because it's the basis of then starting to expand and use it for fancy stuff. So for example, Hooke's law plus modifications, again, plus modifications, leads to a bunch of very exotic but important materials. So things that are glasses, powders, polymers, they all start with Hooke's law as the starter, and then we keep modifying it to make it behave in very weird ways. As an example, Hooke's law, of course, we know and love it in 1D. It says that stress and strain is given by this parameter, the so-called Young's modulus. And the Young's modulus simply says you take stress, you multiply it by this funky factor that's the stiffness of the material, you multiply it by the strain, you get stress-strain relationships, the very beginning of everything. What we don't realize is what happens if it starts to get pretty big deformations? The material is going to start to do funky stuff. It might start to bend, stretch, break, and then snap. It could do all kinds of crazy stuff. So we have to start to figure out how to modify it. But before we can modify it in a logical and systematic way, we have to master where this came from. So packet number 8 goes crazy on that thing. It basically derives Hooke's law in multi-dimensions. So I ask you to please read that for next time in class. It then goes through the whole basic ideas of elastic symmetry, how materials that are anisotropic behave, but are still Hooke's law. So Hooke's law in its very general sense has many different possible material constants. It has a whole matrix of constants inside of it, not just simply one parameter called the Young's modulus. It has at least 21 constants. So if you look at the next upcoming chapter, Hooke's law in its most glorious form is a big nightmare. That thing is 21 constants. It's a 6x6 matrix. It's, mercifully symmetric. So even though there's 6x6 is 36, two of the upper parts of the lower part of the matrix are symmetric. So it's just 6 on the diagonal and 15 off the diagonal, hence 6 plus 15, 21. There are 6 values of strain because there's, the strain is symmetric and the stress is symmetric, but that means there's 6 values of those because they're matrix equations. So remember, stress is sigma 1, 1, sigma 1, 2, sigma 1, 3, and so forth. It's a 3x3 matrix, but it is symmetric. So in fact, we usually write it as a vector, sigma 1, 1, sigma 2, 2, sigma 3, 3, sigma 1, 2, sigma 1, 3, sigma 3, 2. Hence, this thing over here, this vector. And then we do the same thing for the strain, and we have to now connect 6 values of strain to 6 values of stress. And it turns out this matrix comes to the rescue, and that is the so-called elasticity tensor. In 1D, it collapses back to our friend Hooke's law. But in 3D, it's a big mess. So even in the linear case, where it's a linear relationship between a quantity called the strain and a quantity called the stress, it has a lot of constants in it that have to be benchmarked and understood. So if you're doing very careful analyses of a stress-strain relationship in 3D, you've got to go in there and measure all of these 21 constants. That is not an easy thing to do in the lab. That means you have to have 21 measurements to get 21 constants. So we're going to go through that carefully to figure out how that's done. And we're going to then figure out how to calibrate this material for all kinds of different effects. So packet number 8 goes crazy on the calibration and understanding how material laws come into play. And then, of course, we make a revisit to the von Mises criteria, principal stresses, principal strains. We'll find out why those are actually important. We know from already in the previous week that they do exist. They were mildly interesting, but they become extremely important when we start to get to packet number 8, because we're going to find out that those principal stresses come back in material failure. So please read chapter 5 to completion. It's just a couple more pages to it, packet number 8, and then we're going to hit the ground running, and then you'll be completely squared away for assignment number 2. So my colleague, Brian, I believe has deadlines. I mean, because he has to keep the factory moving. When is the deadline for assignment number 2?
Should be next week, a week from today.
We might want to just extend that a bit to, let's say, either Thursday, because I was a little bit behind in the material law stuff. I'll finish that by Thursday. So maybe just to give a little bit more time, I would say, let's extend that to next Thursday.
Sounds good. I'll make an announcement.
Okay, so yeah, make an announcement, because I think some of the people aren't online right now. And so we'll give you just a little bit more time to do that. After this, we'll then go back to some electricity and magnetism, and we'll then introduce the whole concepts of lasers, how those behave, how Joule heating works. You'll then get your next assignment, which builds upon what you're building right now in assignment number 2. And then we'll move on to some more machine learning for other kinds of material or manufacturing of materials. So I'm happy to have maybe 1 or 2 questions. I know it was a lot today, but I think it's some good stuff that'll give you a deeper appreciation of exactly how these basic principles can actually lead to things like, very practical, relationships between, for example, a laser. So very practical things can come out of some very solid fundamental principles. Lasers are with us almost every day in almost every facet of our life. And you can really derive how they impart their heat and things of that sort by resorting to first principles without having to go through too much trouble. So at any rate, I'll close it for today, and I'm happy to answer questions if there are any. All righty then. So have a good evening, and I will see you on Thursday.